Unit 2, Lesson 3, Rational Function. So, things to understand. At the end of the lesson, you are expected to, so first, define rational function. Second, represent rational function through its table of values and graph. Third, find the domain and range of the rational function. Fourth, determine the intercepts, zeros, and asymptotes of rational function. And lastly, graph rational function. So first concept is about rational function. So a rational function is a function in the form of f of x equals p of x over q of x, where p of x and q of x are both polynomials, and q of x is not a zero function. So it is vital or important to understand or to remember that q of x must not be a zero function because it makes the rational function undefined. So here are the examples of a rational function. F of x equals y equals x plus 1 over x minus 2, y equals 2x plus 3 over 4x, y equals x plus 1 all over x minus 3 times x plus 2, and lastly, y equals 4x over x squared minus 25. So the zeros of a function are the values of x which makes the function 0. So the real numbered zeros are also x-intercepts of the function. Okay? So when we are finding x-intercepts, they are also considered as the zeros of the function. And the y-intercept is the function value when x is 0. So for example, we have here a rational function y equals x plus 1 over x minus 2. So we are asked to find the x-intercept and y-intercept and its coordinates. So first one is the x-intercept. So again, in finding x-intercept in any function, not only in the rational, no. So we have to change y to 0 or change the value of y to 0. So we have the rational function, change y to 0. So 0 equals x plus 1 over x minus 2. So cross multiply. So 0 equals x plus 1. Then x-intercept is negative 1. Next one, y-intercept. So in finding the y-intercept, vice versa of the x-intercept, change x to 0. So we have y equals 0 plus 1 over 0 minus 2. So simplify, y equals negative 1 half. So the coordinates are negative 1, 0, and 0, negative 1 half. So next, rational function, y equals to x plus 3 over 4x. So x-intercept, change y to 0, and y-intercept, change x to 0. So after we change y to 0, we have the value of x-intercept, negative 3 over 2, and the y-intercept of undefined. So because 3 divides 0 is undefined. So the coordinates are, for the x-intercept, negative 2/3 over 0. While the y-intercept, no y-intercept, since the y value is undefined. So next one, x plus 1 over x minus 3 times x plus 2. So x-intercept, change y equals 0. So we have x equals negative 1. Y-intercept, change x to 0. So simplify, we have negative 1, 6. So the coordinates are negative 1, 0, and 0, negative 1 over 6. So we have the last rational function, y equals 4x over x squared minus 25. So x-intercept, if y is equal to 0, 0 equals 4x over x squared minus 25, simplify, so we have x equals 0. Y-intercept, change x to 0, so we have the y value of 0. So the coordinates are 0, 0, and 0, 0. So both intercepts are at the origin. So we have this value to summarize the functions and their intercepts, x-intercepts and y-intercepts. So next one, after finding the intercepts, we have now the asymptote. Okay, so asymptote is the line where the graph approaches. Okay, so the line x equals a is a vertical asymptote of the graph of f if f of x approaches infinity or f of x approaches negative infinity as x approaches a. So either from the right or left. So later in the graphing part, we will see the asymptotes and how the graph approaches them. So next one, the line y equals b is a horizontal asymptote of the graph of f if f of x approaches b as x approaches positive infinity or x approaches negative infinity. So in finding the vertical asymptote or the value of the vertical asymptote, the graph of f has the vertical asymptotes at zeros of q of x. So therefore, the zeros of q of x or the value that makes q of x 0 is the vertical asymptote. While the horizontal asymptote, we have three cases. So the graph of f has at most one horizontal asymptote which varies with the degree of p of x and q of x. So first one, if n is less than m, so n is the degree of the numerator of the leading term, while m is the degree of the denominator of its leading term. So the graph of f has the line y equals 0. So basically, if the degree of the numerator is less than the denominator, the graph has a asymptote or has a horizontal asymptote of 0. So next one, if the numerator and denominator has the same degree of its leading term, so the horizontal asymptote is the quotient of its coefficient. And lastly, if the numerator degree is greater than the degree of the denominator, so the graph has no horizontal asymptote. So it has an oblique asymptote. Okay? So for us to be able to understand, so here are the functions again, and we will find their asymptotes. So first one, y equals x plus 1 over x minus 2. So again, in finding the horizontal asymptote, we need to look at the leading term of the numerator and denominator. So in this case, we have x and x. Okay? So both numerator and the denominator has the leading term of x, which has a degree of 1. So therefore, we have n equals m, which is the second case. So therefore, we will get their coefficients, which is 1. So 1 for the numerator and 1 for the denominator. So divide that. 1 divide 1 is 1. So therefore, we have y equals 1. Okay? So next, vertical asymptote. It is the value that makes the denominator 0. So in this case, x minus 2. So what makes the denominator 0? Obviously 2. Okay, so x equals 2. So next one, second rational function. So 2x plus 3 over 4x. So horizontal asymptote, the leading terms for the numerator and denominator, 2x and 4x. So both has a degree of 1. So 2x raised to 1 and 4x raised to 1. So therefore, we will get the coefficients. So numerator, we have 2. Denominator, we have 4. Divide them 1/2. So y equals 1/2. And the vertical asymptote, what makes the denominator 0? So 4 times x. So think of a number. If multiply by 4, the answer is 0. So obviously it is 0. X equals 0. Third, y equals x plus 1 over x minus 3 times x plus 3. Okay? So in this case, horizontal asymptote, we have x and we will multiply first the denominator. So we have x squared. Okay? So x and x squared. The numerator exponent is less than the exponent of the denominator. So we have case number 1. So therefore, we have the horizontal asymptote of y equals 0. And the vertical asymptote, what makes the denominator 0? So we have 2, 3, and negative 2. And lastly, the last function, so we have 4x over x squared minus 25. So again, case number 3 in which the numerator degree is less than the denominator degree. So we have y equals 0. And the vertical asymptote, the value that makes the denominator 0, so we have 5 and negative 5. Since x squared minus 25, sum and difference of 2 squares, so we can expand it like x plus 5 times x minus 5. So therefore, we have two vertical asymptotes, negative 5 and 5. So after getting the intercepts, asymptotes, next we will find the domain. The domain of the function is a set of all values that the variable x can take. Okay? And next one, the range of the function is the set of all values that f of x can take. Okay? So for this one, we will just base the domain and range to its asymptotes. Okay? So for the domain, we have to base the domain to the vertical asymptote, while the range, we will base the range to the horizontal asymptote. Okay? So the asymptotes will become the restrictions for the domain and range. So for example, y equals x plus 1 over x minus 2. So a while ago, we have a horizontal asymptote of 1 and vertical asymptote of 2. Okay? So therefore, for the domain, since it's based on the vertical asymptote is 2. So we have from negative infinity to 2, union 2 to positive infinity, or x, set of x, where x is an element of real number such that x is not equal to 2, since 2 is the asymptote or the vertical asymptote. While the range, we will restrict the range based on the horizontal asymptote, which is 1 a while ago. Okay? So negative infinity to 1, union 1 to positive infinity. So in set, we have y, the range is equal to y, element of real number, such that y is not equal to 1. Okay? So to understand, we just need to write x or y, element of real number, such that x or y is not equal to the asymptote. Okay? So that's it. The second one, 2x plus 3 over 4x. So domain based on the vertical asymptote. So we have a vertical asymptote of 0. So therefore, negative infinity to 0, union 0 to positive infinity. Okay, so x, element of real number, such that x is not equal to 0. Then the horizontal asymptote, so we have 1/2 a while ago. So from negative infinity to 1/2, union 1/2 positive infinity. So y is an element of real number such that y is not equal to 1/2. So we can see that the asymptotes becomes the restrictions for each domain and range. Okay, so it is just easy. But not all the cases is just like that. Okay, so we can see that in our fourth example. So third example first. So we have x plus 1 over x minus 3 times x plus 2. So since we have two vertical asymptotes, we have negative infinity to negative 2, union negative 2 to negative 3, to 3 positive rather, union 3 to positive infinity. Okay, or x is an element of real number such that x is not equal to negative 2 and 3. Okay, since negative 2 and 3 are the asymptote of vertical. Next, horizontal, so we have 0. So we have negative infinity to 0, union 0 positive infinity. And y, element of real number such that y is not equal to 0. On next one, fourth example, 4x over x squared minus 25. So we have the vertical asymptote of negative 5 and 5. So therefore, we have negative infinity to negative 5, union negative 5 to 5, union 5 to positive infinity. Or x, element of real number such that x is equal to, or x is not equal to positive negative 5. And the range, so we have the horizontal asymptote of 0. Since we are under case number 1, degree of numerator is less than the degree of denominator. So 1 is less than 2. So we have automatically 0 horizontal asymptote. But the intercepts of the given rational function is 0, 0, and 0, 0. So we can say that the graph must pass 0. So therefore, the horizontal asymptote will be ignored. So the range is negative infinity to positive infinity. So y such that y is an element of real numbers. Okay? And that's how we get the domain and range. So always remember that finding a domain and range is connected in their asymptotes. Okay? So the asymptotes become the restriction for domain and range. So vertical asymptotes become the restrictions for the domain, and at the same sense, horizontal asymptotes became the restrictions for the range. Graphing rational function. So again, we have the first rational function given. So we have now the information a while ago, the intercepts and the asymptotes. So x-intercept negative 1, 0, y-intercept 0, negative 1 half, horizontal asymptote y equals 1, and vertical asymptote x equals 2. So next thing to do is we will construct a sign table for this given function. So since we have two expressions, x plus 1 and x minus 2, so therefore the critical points are x equals negative 1 and x equals positive 2. So we have now three regions. So x is less than negative 1, x is between negative 1 and 2, and lastly, x is greater than 2. Okay? So the two expression, x plus 1 and x minus 2. And as a whole, x plus 1 over x minus 2. So we will now get the test points. So the test points are the values within each region. So we have x equals negative 2 since negative 2 is less than negative 1. We have x equals 0 since 0 is between negative 1 and 2. And 3 since 3 is greater than 2. So now let's test the points. So negative 2 plus 1 is negative 1, so we have negative. 0 plus 1 is 1, so we have positive. 3 plus 1, 4, so we have positive. Next one, negative 2 minus 2, negative 4, negative. 0 minus 2, negative 2, negative. And 3 minus 2 is 1, positive. Then, multiply. So negative 1 negative times negative, positive. Positive times negative, negative. Positive times positive, positive. So this signs tells us the behavior of the graph. Okay? So positive means the graph is above the x-axis, while negative states that or tells us that the graph must be below x-axis, and positive again above x-axis. So therefore, the region x is less than negative 1 is above, x between negative 1 and 2 is below, and x greater than 2 is above. So we can see it in the graph. So first thing to plot are the asymptotes. So we have y equals 1. So y equals 1. So broken line. So we will represent the asymptotes as broken line. So we have first asymptote y equals 1. So the y-axis 1. So this part. Next, vertical asymptote x equals 2. So x-axis 2. So we have this horizontal vertical line. And the intercepts. So x-intercept negative 1, 0. So negative 1, 0. And 0, negative 1 half. So 0, negative 1 half. Okay? So first region is x is less than negative 1. So negative 1 to negative infinity. Okay? So the graph must be above x-axis. So we can see that the graph is above the x-axis. Next, x is between negative 1 and 2. So negative 1 and 2. So this part. So the graph must be below x-axis. So extend the line, but it must connect to the other intercept. Then extend. Okay? And lastly, the part x greater than 2, so 2 to positive infinity, then above x-axis. So in rational function, we can always see reflections. Okay? So this graph must be reflected on this part, okay? But above x-axis, okay? So this one, you can see this one is being reflected. So now this is the graph of y equals x plus 1 over x minus 2. So the domain, a while ago, domain is x element of real number where x is not equal to 2. And range is y is an element of real number such that y is not equal to 1. So 2 is the vertical asymptote and 1 is the horizontal asymptote. So next one, y equals 2x plus 3 over 4x. So we have the informations a while ago. So negative 2/3 0, x-intercept, y-intercept none since it is undefined. Horizontal asymptote y equals 1/2. Vertical asymptote x equals 0. So again, the critical points or the regions. So we have two critical points, negative 2/3 and 0. So we have three regions since we have two critical points. So less than, x is less than negative 2/3. X is between negative 2/3 and 0. And lastly, x greater than 0. So the test point, the expression, we have 2x plus 3, 4x, and as a whole, the rational expression. Now, the test points, x equals negative 2, x equals negative 1/2, and x equals 1. So these values are within the regions. So now let's check. So negative 2 times 2, negative 4 plus 1 is negative 1. So negative 1/2 times 2, negative 1 plus 3 is 2. So positive. And 2 times 1, 2 plus 3 is 5. So positive. Next, 4. So negative times 4, negative 8, negative. Negative 1/2 times 4, negative 2. So negative. And 1 times 4 is 4, positive. Now multiply. Negative times negative is positive. Positive times negative, negative. Positive times positive, positive. So therefore, the region x less than negative 2/3 must be above the x-axis. X between negative 2/3 and 0 must be below x-axis. And lastly, x greater than 0 must be above the x-axis. So first, the asymptote y equals 1/2. So 1/2. 1 and 0 in between, 1/2. So the broken line. And next one, 0. So at the origin, then broken line. Then the region x less than negative 2/3. So negative 2/3 is here. So above. So above the x-axis. Next, between negative 2/3 and 0. So negative 2/3 and 0. So below the x-axis. Okay. And lastly, the region greater than 0. So this part. So this graph must be reflected. So we have this one. Okay. So this is the graph of y equals 2x plus 3 over 4x. So domain and range a while ago. So domain, x element of real number such that x is not equal to 0. And range, y is an element of real number such that y is not equal to 1/2.